Good morning, chemistry students. My name is Mr. Adam. This is chemistry. Today is the 13th of May. It is a Wednesday, and it is a day 5 in our rotation. So, good morning, everybody. I hope you're having a great day. Yesterday, obviously, we finished up with Unit 2, Section 2. So, we either did our Unit 2, Section 2 quiz, or we submitted our Build a Molecule activity. So, we are done with those, and we're moving on to our last section in our Smells Unit, Unit 2, Section 3. Okay? So, if you still need to finish those, either of those, the quiz or the Build a Molecule, for any reason, please let me know. Please just send me a quick email. Tell me that you're still working on those for whatever reason, and I'll make sure to look out for your late work whenever you get that turned in. Okay? So, with that being said, we're moving on to a new section, like I said, Section 3. And in this section, we're talking all about molecules and their attractions. So how molecules are attracting to each other, right? How they're interacting with each other. So molecules, you might hear this phrase in science or in life a lot. Molecules don't exist in a vacuum, right? They're not just by themselves. They interact. And no, they don't socially distance very well. So these molecules move around, and as they do, yes, they're going to go into our noses and interact with smell receptors and, link up there, but they're also going to interact with the other molecules around them. So if you have a molecule of water, it's going to interact with other water molecules. If you have a molecule of nitrogen in the air, it's going to interact with other molecules, the other nitrogens and the other oxygens and the other CO2s, right? So all these things are always constantly interacting with each other. And their interactions actually determine a large amount of what we see in the real world, with what phases they're in, how they behave, how they can be smelled or not smelled, right? So these interactions determine a ton of what we actually notice and what we actually see about molecules. So, when determining how different molecules will interact, we have to consider a couple new concepts. And we're going to start talking about some of these concepts today. The first concept we're going to talk about is super important for us. That concept, everybody, is called polarity. Look at this word. This is polarity. You're going to read this in your reading, and Miss Marnick's going to talk about it in her video, and you're going to read about it in the notes. But this term polarity is going to be super important for us, so it's very important that you understand what that means. I want you to look at this word for a second and break it down a little bit. What do I have underlined here? The word polar. Okay, what does polar mean? I know what a polar bear is. It doesn't tell me much about how molecules interact, though, right? So what do I think of when I think of polar or poles? Where have you heard of poles, P-O-L-E, before? Have you looked down the drawing? I have two examples of where we've probably talked about poles before, right? This badly drawn thing here is supposed to be a magnet, right? So a magnet, we should know, has two poles. It's got the North Pole and the South Pole. And the North Pole might be positively charged, and the South Pole is negatively charged. So in poles, you can have opposite charges. And what do we know about opposite charges? Opposites should attract. So when you have opposite charges in magnets, they should attract, okay? Where else have we heard of poles? We've heard of poles in the North and South Pole, right? So the North Pole, where Santa lives, and South Pole is where Antarctica is and all the penguins and everything are. Don't quote me on that, I don't know animal habitat super well. But again, in the poles are extremes of the planet, and they're both associated with some sort of magnetic pole. If you have a compass, it always points to north because it's magnetically attracted to the North Pole. Okay? So when we talk about poles and polarity, we're talking about magnetic attractions, electric attractions. With these attractions, we have a positive and a negative, and we know that like charges are going to repel and opposite charges are going to attract, right? So when we talk about molecules being polar, we're talking about molecules having charges. All the polar means is that something is charged. So this molecule of water, H2O, right, has charges on it. If you draw the Lewis structure and you know what shape it takes on, you know it's a bent shape, and you know this oxygen has two lone pairs of electrons. Now, what charge are electrons? We talked about this a long, long time ago. We said protons are positive, neutrons are neutral, electrons are negative. Okay. So this oxygen here has lone pairs of electrons. And so, because it has extra electrons, it's going to take on what we call a partially negative charge. Okay? A partially negative charge, and then the hydrogens, which don't have a lot of electrons because oxygen's taking them all for itself, is going to be partially positive charge. So if I have partially negative charges and partially positive charges, what are those going to do? They're going to attract, right? They're going to be able to attract each other. So let's think about this for a second. I'm saying that water molecules are charged. They have a charge. Well, Mr. Adam, I don't get shocked every time I touch a water molecule. Correct. That's because they have positive and negative charges in them and they balance out. Well, Mr. Adam, I can't attract a stream of water with a magnet. Can't you? Have you ever tried that? Have you ever tried to flow a thin stream of water and see if it moves when you put it next to a charge or electricity or a magnet? We're about to go do that. So we're going to see what actually happens when you have these water molecules that I'm telling you are supposedly charged and put them next to some sort of electrostatic electricity or a magnet, right? So we're going to go over to my sink. We're going to do a quick demo. A very, very technical lab station over here. I mean, not my sink. My kitchen sink. So we'll try to set this up, get it so we can see this stream of water. That should work. Okay. So, hi guys. So today we're going to actually look at what happens when we expose a stream of water to charges, right? To charged particles. So I have here just an ordinary balloon. I'm going to take my new fuzzy head that has very much less hair than it used to and start rubbing it. And when I do this, what am I actually doing besides looking stupid? I'm putting charged particles on this, right? I'm putting static electricity on this balloon. So right now there's static electricity on this balloon. You can kind of see it make my hair stick up a little bit maybe. There's static electricity on this balloon. That static electricity is made of electrons, which are what charge again? Negative. So there are a lot of negatively charged particles on this balloon right now. And so, if I turn on the water, in the stream, that's pretty good. If I turn on the water, I rub my balloon on my head, get some negatively charged particles on it, and put it next to the balloon, you can see, well, let's see if we can get a good angle for this. You can see, as I put it closer, what does the water do? The water actually moves. I'm actually bending the water, and it's less dynamic on the video for sure, but there we go. You can see as I get the balloon closer, I'm not touching that stream of water at all. I'm not contacting with anything, I'm not adjusting the water stream. I'm just bending that water. I am, as you know, one of my favorite shows is Avatar, The Last Airbender. I am currently being a water bender. Literally bending water with this static electricity. That was a good one. Right? So what does that tell us? I don't know. I think that's pretty cool, but what does that actually tell us? It tells us that the charge that I just put on the balloon, let's sit back up. The charge that I just put on the balloon, which was made of negative charges, negative electrons, was able to move those water molecules, which means that they have to have some sort of charge within them that they can be moved by. So Ms. Marnick does an awesome job talking about this in her video. So I want you to go watch that, check that out, see what she tells you exactly about how water molecules look, why they line up, and why their charge is affected by that balloon. Okay? Guess what? I have a second demo for you today. So we talked about polarity. We said that a polar molecule is going to have charges. What about a molecule that doesn't have charges, right? What about what we would call a non-polar molecule? Well, something like oil is going to be a non-polar molecule, and that's not going to have charges. And so it's not going to be affected by that balloon, right, with the static electricity on it. Not only that, but polar and non-polar molecules are going to be charged versus not charged. They're not really compatible. I know we said opposites attract, but in this case, these molecules are so unalike that they're not going to interact pretty much at all. They're not going to dissolve within each other. We have a phrase that we say in life and in chemistry, like dissolves like, right? Some things don't mix, right? What doesn't mix? Oil and water. Right, so oil and water do not mix. So we have some oil and we have some water. So we know these don't mix. We've talked about this before, but the reason they don't mix is because oil is what we call a nonpolar substance. So we pour some oil in there. Oil is a nonpolar substance, which means it doesn't have any charges associated with it. Water, on the other hand, is a polar substance. So it does have charges. So we'll throw those in there. Oh, Mr. Adam, you lied to me. They mixed. Or did they? So what you should start to see in this jar here, and you've probably seen this before, is that the oil starts floating to the top because it's less dense, and the water sinks to the bottom. And you can see that there's kind of some bubbles going on in here. Let's bring this right up to the camera. There's some kind of bubbles going on in here. That's water dissolved in the oil, but it's starting to separate, right? So you're starting to see the water sink to the bottom and the oil float to the top. They're starting to separate. Crazy, right? I know you've seen that before, but the reason behind that is this. Oil is a nonpolar substance. So that means it will not dissolve. It will not mix with any polar substance like water, like ethanol, like ammonia, any other polar substance will not dissolve with oil. So, think about it. The next time you try to mix oil and water, think about why that is. It's because they're two different kinds of substance. One is polar and one is non. Miss Marnock is going to do a great job of explaining this to you, breaking down the chemistry of why things would be polar versus non-polar. But I hope you enjoyed some demonstrations today. I really hope you watch this and get to check these out and see a little bit of chemistry in action. I know it's been a while. But this is one of my favorite topics to talk about, to discuss polarity and non-polarity and kind of see the consequences of those, because we can see it in our real life. And if you get a chance, if you have a comb at home and have long hair from that quarantine, right? Go ahead and take a comb, get some static electricity on that comb, put on a thin stream of water in your faucet and see if you can bend water too. It's pretty cool. It's something you can definitely do at home. So check it out, give it a shot. I will see you all tomorrow. Have a great day. I'll see you tomorrow. Let's get a 1, 2, 3. Clap on me.